Okay, hello everyone. Today we will learn about continuous variables and their probability distribution. Um, Before we start, I'd like to briefly go over something that we've learned last week on probability distribution for a continuous random variable. The definition 4.1 tells about distribution function of y, um, uh, large fy. The distribution function of y is this one. Fy is probability of random variable y is smaller than or equal to y. This is definition of distribution function, and in definition 4.2 we define a random variable y, continuous random variable y. What is continuous random variable? By definition, a random variable y with distribution function fy is said to be continuous if fy is continuous for the domain of y. Previously we have learned about discrete random variables, and for discrete random variables, the distribution function is always a step function. For discrete random variables, the distribution function always have a probability math on discrete points. So there's discrete points here, and for discrete random variable, there's always jumps at each point, and it reached to probability of 1. This is the discrete random variable case, and on the other hand, for the continuous random variable case, it's continuous line. This is a continuous random variable, and the important thing is that we call the small fy as probability density function, and we can calculate the probability of y is less than or equal to small y. This is fy. We can calculate it by integration from minus infinity to y. Let's say y0. Fy dy, and this is what it shows. So to calculate probability of y is smaller than or equal to y0, we can get this probability by getting integration of the probability density function fy, and that's yeah, we can calculate fy0 with its probability density function. Okay. Let's solve the example 4.2. Suppose that fy is defined like this, and find the probability density function for y and graph it. Okay, to calculate probability density function, we can get the derivative of fy. So we want to get f derivative of y with respect to y, and this is 0. Derivative of 0 is 0 for y less than 0, and derivative of y is 1 for y is greater than or equal to 0 and less than or equal to 1, and derivative of 1, this is also 0. So for y is greater than 1. So if you draw the graph for it, it's like for y is less than 0, it's 0, and from y is 0 to 1, it's 1, 1, and for y is greater than 1, it's 0. So so this is the graph for this example. Okay. Okay, let's move on to example 4.3. let y be a continuous random variable with probability density function given by here. So fy is probability density function, and the problem is find fy, find distribution function of y, and graph both density function and density function, the distribution function. Okay, let's draw the probability density function first, and here fy is defined on the whole interval on y, and actually it's defined on 0 to 1 interval as 3y square and 0 otherwise. So let me change the color with blue, and it defined as 0 for this interval, and from 0 to 1 it defined as 3y square, and as you know, the y square it looks like this from 0, so 3y square is this, and from here it's again 0. And okay, let's and what is the distribution function? Distribution function of y is probability of random variable y is smaller than or equal to small y, and actually this is we can calculate it from by integrating the probability density function. So it's the area um, of the fy. So if our fy is something like this, then the and here if it is y0, and then fy0 is the area of this, if this is fy. Okay, so we can calculate this probability with integration from minus infinity to y, fy, fy dy. And actually, since the density function is defined on 3 different areas, like the density function is defined on 3 different areas when y is less than 0, when y is greater than or equal to 0 and less than or equal to 1, and when y is larger than 1. So it defined in 3 area, and when y is less than 0, the point is here. So integrating from minus infinity to here, it's 0. So this part is 0. So when y is less than 0, integrating minus infinity to y, fy is 0 dy. So this is 0. So this is 0. And for y is between 0 and 1, then this part becomes minus infinity to 0, it's 0 dy plus, and from 0 to y, it's 3y square, 3y square dy, and this guy becomes y third, and from 0 to y, and this is y third. So this part is y third. And what about this part? It is integrating this function, and y is located here. So for this part, it's minus infinity to 0 and integrating 0 dy, and from 0 to 1, it's 3y squared dy, and plus from 1 to y, it's again 0 dy. And so this part is 0, this part is 0, and this part is y third 0 1, which is 1. So this part is 1. And you can graph this, and the graph of this is Here is y, and here's fy, and if it is less than 0, it is 0. I will change the color as red again, so 0. And for 0 to 1, it's y third. And for y is, if for y is greater than 1, it's 1. So this is the graph of fy, the distribution function of y. So this is density function, and this is distribution function. Okay. In definition 4.4, we talk about quantile. Let y denote any random variable, and if p is greater than 0 and less than 1, the pth quantile of y, denoted by pi p, is the smallest value such that probability of y is less than or equal to pi q is equal to f pi p is greater than or equal to p. Actually, this is typo. This should be p, pi p, and um, and this is for any random variable of y, and if random variable y is continuous, then pi p is the smallest value such that f pi p is greater than probability of y is less than or equal to pi p and equals p. Okay, so let's look at the definition this first for the continuous case, and then think about this one, the upper one. So let's look at this. So let's say the random variable y is from continuous distribution. So this is density function of y, and if the area till here, if it is 0.5, if the area until here is 0.5, then this point is pi 0.5, and at this point, so here it is probability of y is less than or equal to pi 0.5, and this is 0.5. So this is definition for this, and for discrete case, discrete and actually before we talk about discrete case, the distribution function for this case is that it looks like this. The distribution function fy looks like this, and for this fy, if it is 0.5 here, then this is actually the same as pi 0.5. Okay, so here's here's density function fy, and in fy, the quantile, to calculate the quantile, then you integrate from minus infinity to 5.5, and if the integration, the value is 0.5, then that point is the 50% 50 percentile of y. And if you look at the distribution function of y, from distribution function, if you find the point of 0.5, if your distribution function have the value 0.5, then that position is the 50% 50th percentile of y. Okay, and this is for continuous case, and for the general case, there's jump in the distribution function. So in the continuous case, the distribution function is continuous. However, if it is not a discrete, not a continuous case, sometimes there's jumps. Sometimes there's jumps. Let's say it is 3 over 1, 1 over 3, and there's jump to 2 over 3, and like this. In this case, you don't have 50 percentile. However, by definition of let's say, by definition of here, 0.5. Okay, so let's say this point is 0.5. Then at f 5.5 is 2 over 3, which is greater than or equal to 0.5, and this is the smallest value, such that this is the smallest value that makes this possible. If 5.5 is a little bit greater than here, it would be it will hold this equation, but this 5.5 is the smallest value. If it is a little less than this value, then the f of that value would be 1 over 3 or less than 1 over 3. So so for the general case, we use this definition for the quantile. Okay, and the quantile that we used a lot is 25% quantile, or 50% quantile, or 75% quantile. And to calculate these values, these quantiles, you can just if you have distribution function, you can calculate it from the graph, or even if you have the probability density function, you can also calculate the quantile value from the integration. And note that 5.5 is the median of the random variable. Okay. Next one is theorem 4.3. If the random variable y has density function fy and a is less than b, then the probability that y falls in the interval a to b is this. And to calculate the probability of from a to b, you can calculate it from the integration from a to b of probability density function. And actually, the derivation of this, it's kind of intuitive. To calculate the probability of this thing, you get the probability of this by integrating the density between the interval from a to b. This is and the derivation, actually, you can think about that the set, if you divide this as two intervals, this and this, the combined set of for the set from minus infinity to a, y is less than a, this set in union of this set, union of these two sets is actually this set, y is less than or equal to b. So and we can calculate this two sets. And these two sets are disjoint. So what it means is that the probability of y is less than a plus probability of a greater than or equal to y, b is equal to probability of y is less than or equal to b. And here, actually, for the continuous case, at a point, there is no probability mass. So the y is less than a. Actually, this is equal to probability of y is less than or equal to a. Uh, and this is, by definition, integration of minus infinity to a f y dy, and this part is integration of minus infinity to b fy dy. So this part is this one minus that one. So probability of a is y is greater than or equal to a, less than or equal to b. This is the integration of minus infinity to b fy dy minus infinity to a fy dy. And actually this is from a to b fy dy. Okay. Let's solve example 4.4. Given fy is cy square for y is defined on 0 to 2 and it is 0 elsewhere. Find the value of c for which fy is a valid density function. Okay, so let's graph it first. From 0 to 2. From 0 to 2, it's cy square, and obviously c is greater than 0, because if c is less than 0, the shape look like this, but the density function must greater than or equal to 0. So c should be greater than 0, and for other areas it defined as 0. So and to make this function as probability density function, then the integration from minus infinity to infinity fy should be 1. So it is actually enough to show that 0 to 2 fy equals 1, because other areas fy is 0. So it looks like 2, it's 1. Okay. So to calculate this one, from 0 to 2, cy square dy, and this is c times 3 y third, and from 0 to 2, and this is c over 3 8 minus 0, and so this is 8 over 3 times c, and to make this as 0, c is 3 over 8. Okay, so we calculated the c. Next example is example 4.5. Find probability of y is greater than or equal to 1 and less than or equal to 2 for example 4.4. Also find probability without equal sign. So okay, in the previous example, the probability density function fy is 3 over 8 y square, for y is this and 0 otherwise. Okay, and we want to calculate probability of this and that. Okay, let's go this one first. Probability of y less than or equal to 2 is integration of from 1 to 2 3 over 8 y square dy, and this is 1 over 8 y third over 8 and 2 1, which is 1 minus 1 over 8, which is 7 over 8. Okay, and about this one, what would be the probability of y equals 1? Actually, for this one, what would be the area? Let's say this is probability density function. And what is the area of y equals 1? And actually this is 0. So this is 0. So for the continuous random variable case, if it is just constant, then probability for that random variable getting the constant, it is 0. So probability of y is greater than 1 and less than 2 is again 7 over 8. Okay. And here are homework problems for chapter 4.2. Now let's move on to expected values for continuous random variable case. Let's look at the definition first. Definition 4.5 tells about the expected value of y for the when y is continuous random variable, and which is expected value of y. It is integration from minus infinity to infinity y times fy dy, and actually this is the similar extension from discrete probability. For the discrete probability, it is the expected value was y py. Yeah, this one. This was expected value of y for discrete case, and yeah, actually, yeah, we can see the similarity. Okay. The extension for the function of random variable is also very similar. When we are calculating expected value of a function of random variable, and actually this g of y is also a random variable. So the random variable y, this is from set to real value, and this g function, this function g, is from real value to real value. So g of y is from set to real value. So, and also the probabilities related to y is actually same. So the integration from minus infinity to infinity, and we need random variable here, which is g of y, and fy dy is the related probability for random variable gy. So this is kind of general extension. And the proof is also similar to that of discrete case. Okay. Okay, and theorem 4.5 also can be proved similarly like we proved for discrete random variable case. which is this. Let C be a constant, and let gy, g1y, g2y, and these are random variables, be function of constant random variable y. Then the following results hold. The first one is expected value of constant is constant, and the second one is expected value of constant times function of random variable. You can get the constant outside of the expectation. This is the second one, and the third one is expected value of function of random variables. You can calculate each expected value of random variables first, and then sum them up. These are same results, just like discrete random variable cases, and also the proofs are very similar. For example, for the expected value of C, this is actually sum of integration of minus infinity to infinity C times Fy dy, and actually this constant C is not depend on this integration, so you can get the constant out, Fy dy, and by the definition of the probability dense function, this one is 1, so it's C times 1. And for the second one, actually this is also very similar. Expected value of C times gy. This is expected integration minus infinity to infinity C gy Fy dy. Okay, and from here, this C, constant C, is do not depend on this y, so C can go outside of this integration, minus infinity to infinity g of y times f of y dy, and this is C times expected value of g of y. Okay, and for the third one, I think probably you can do it by yourself. So the third one, this is exercise for you, and after showing these three equations, actually you can also derive this one, which is also derived previously for the discrete random variable case, and this one also holds for continuous random variable case. Okay, you can do it by yourself, and actually the proof is same as discrete case. Okay. Let's move on to example 4.6. In example 4.4, we determined that Fy is 3 over 8 times y squared for y is greater than or equal to 0 and less than or equal to 2. Fy is 0 elsewhere is a valid density function. If the random variable y has this density function, find mu and sigma square, the expected value of y and variance of y. Okay, so let's do it one by one. Mu is expected value of y, and from the definition, this is minus infinity to infinity y Fy dy, and from here Fy is 0 elsewhere, and for from 0 to 2 it is this one. So the outside of 0 to 2 interval, it is 0, and y times from 0 to 2 it is 3 over 8, and y second dy, and this one is actually 4 over 1 y fourth and times 3 over 8 and 0 2, and this is 2 2 4 and times 3 and so, and it is 3 over 2 minus 0. Okay, minus 0. Okay, 3 over 2. So expected value is 3 over 2, and what is the variance? Vy, which is e y square minus e y square. So actually this is mu square, and so let's calculate e y square. From 0 to 2, y square 3 over 8 y square dy, and this is 1 over 5, 1 over 5, 3 over 8 y fifth, and 0 to 2, which is 5 times 2 to 3, 2 to 5, 3, which is this one. Okay, and so variance of y is 12 over 5 minus 9 over 4, and you can calculate it, and expected value is this one. Okay, this is proof for example 4.6. Okay, next one is actually exercise problem 4.34, and this is entrance exam problem for the graduate school in statistics department. So I think it would be good for you to know how we can prove this one. So let's look at it. Suppose that y is continuous random variable with density function fy that is positive only if y is greater than or equal to 0, and if fy is the distribution function, show that this one. And actually you probably remember that we proved this one. Expected value of y is sum of k equals 1 to 0 to infinity, 1 to infinity, and probability of y is greater than or equal to k. For discrete random variable case, probably you maybe remember this one. And actually this one is the similar extension for continuous variable case. You may be check that this one is actually probability of y is greater than or equal to small y, and you can see that this is the extension from the discrete case. Okay, then how can we prove this? Let's use hint to prove this problem. Okay, for expected value of y, this is from 0 to infinity y times fy dy, and here from this we can replace y with another integration from 0 to y dt fy dy. And actually this is double integration from dy 0 to infinity and dt from 0 to y, and the function is fy, and we have dt dy. Okay, and from here actually the situation is like this. This is axis for t, this is axis for y, and for dy is defined from 0 to infinity, dy is from 0 to infinity, and for dt is from 0 to y, so dt is 0 to y, which is this one. So domain is this one, and the function fy, we don't know the shape. Let's see, the shape looks like this. Then this shape is on this interval. Okay, and here, if we want to change these two, dt and dy, let's see. So here's t, t and y. So dy is from 0 to infinity, and t is from 0 to y. So this is this one. And if we change the integration to dy dt, then dt is again from 0 to infinity, dt is again 0 to infinity, and dy is from y to infinity, or t to infinity, t to infinity, and the inside is fy. Okay, and now let's see the inside part. This part is probability of y is greater than or equal to t and dt. And actually, this is the proof. You probably see that the similarity of this one and this one. This one is star, and actually this one is star. They are the same thing. If you change this t with y, they are same. So this is proof for the example problem 4.34. And here are homework problems for chapter 4.3. Okay, thank you.